Okay, so in today's lesson, what we're going to learn is what the graph of the exponential function looks like. In the previous two exercises, you've done a lot of the mathematics sides of exponentials. I'm saying exponentials because it relates to the word exponent, which relates to indices. So the graph of the exponential function has the rule y equals a to the power of x. Now this isn't the same as y equals x squared, which we're more familiar with. For y equals x squared, our variable is the base, not the index. We're going to be learning about what happens when the variable is in the index. So to do that, we're going to make up the table of values. To make our table of values, we'll start from the negative side, and we'll start subbing in. Now for the first one, I'm going to write out the steps in case you don't know what it is right away. So we've got 2 to the minus 3, which is the same thing as 1 over 2 to the 3. That's a negative index, which is 1/8. So we get 1/8 for the first value of y. You can do the same for the other values of y, where there are negative indices, and you find you get a quarter, a half, and when x is 0, 2 to the power of 0 is 1. Then 2 to the 1 is 2, and 2 to the 2 is 4. So as you can see, with each step across, we're doubling, no, we're not doubling, yes we are doubling, we're doubling our y value, and you can see that from the base. That base of 2 tells us we're doubling each time. Conversely, if we're going backwards, can you see that it's halving each time? Okay, so hopefully we can see some kind of pattern showing up in our graph. So let's place our coordinates. Starting from -3, we get 1/8, which is very close to our x-axis. Just place a dot there. Then when x is -2, y is 1/4. When x is -1, y is a half. And when x is 0, y is 1. And we can place the others in when x is 1, y is 2. And when x is 2, y is 4. And we see this kind of curve that seems to be curving upwards. That's telling us that for every x value that we're increasing by, our y value is being doubled. I'm going to give you some time to copy that down while I set up. This is room 2.4. All that. Okay, so I'm going to place the exact same graph onto the projector. Would you agree that these look the same? They're the same? Okay. So what I'm going to do is compare the graph of y equals 2x with another graph, and I'm only going to change another number. So there's nothing you need to copy down at the moment, but I'll label this y is equal to 2 to the power of x. Now, I'm going to try and plot y equals 5 to the power of x. So you can predict what the graph should look like. If it was 2 to the power of x, we're doubling each time. If it's 5 to the power of x, then we're multiplying by 5 each time. Do you think the curve would be more steeper or more flatter? What do you think? Steeper or flatter? We're times 5 each time. Is the number increasing faster or slower? Faster, so it should be steeper. Let's see if it actually turns out to be steeper. Y equals 5 to the power of x. Can you see how that's steeper? Okay, so the first thing you should learn is that the base tells you how steep the graph is. More technically, the technical term that you'll explore more in Year 12 is that base actually gives a dilation in relation to your y-axis. So it's a dilation that's closer to your y-axis. I'll place one more on there. This time it's y equals 1.5 to the power of x. So if I place 1.5 to the power of x, we should see a graph that's not as steep because the number isn't as increasing as quickly. 1.5 to the power of x. Okay, that's the purple line, so it's not increasing as quickly. Right, now on your graph, what I will ask you to do is make a sketch. First label your graph with y equals 2 to the x, and then make a graph on top of this for y equals 5 to the x. If you notice, both graphs pass through the same y-axis. You can compare it on the projector as well. So make sure it passes through the y-intercept of 1, and then label y is equal to 5 to the x. Okay, so I'm going to delete the two graphs, and then I'm going to make one where our value of a, which is the base, is not more than 1. Let's call it 0.5. Y equals 0.5 to the power of x. So I'll write it down here, 0.5 to the power of x. I'm going to ask you all to think for a moment. For the previous few graphs, we were doubling or multiplying by 5 each time. What does this tell us? Smaller? By how much each time? Each step that we go, what are we multiplying by? Half. So we're halving each time. So take a moment to just guess what the graph should look like once I plot this on there, and then check your own answer. So it's 0.5 to the power of x. Okay. That purple graph shows that it's going downwards. It's going downwards because we're taking our number, whatever we start off with, and halving it each time. That basically means that we're halving it. So one more graph that I'm going to ask you to place on top of your own. This is going to be y equals, and I'm going to use the fraction symbol, a half to the power of x. A half, because we're halving each time. So if we're going forwards, our number is getting smaller and smaller. Conversely, if we're going backwards, that implies our number should get bigger and bigger. Okay, now I'm going to place one more on the board, which is y equals 2 to the power of negative x. I haven't shown that before. But these two equations, 0.5 to the x and 2 to the negative x, they're actually related. So I'll give you a moment to guess what the graph would be if I plot 2 to the negative x. Okay. Just take a moment to look at these two. In fact, I'll write them next to each other, a half to the x and 2 to the negative x. They're related. George, what do you think?
Well, since that's actually 1 over 2 to the power of x.
1 over 2 to the x?
Yeah. Would it be on this curve, on the same type of curves?
The same type of curve. Can you see how these are the same? 2 to the negative x and a half to the x, they should be the same thing because we've got a negative index, which implies that our base belongs in the denominator. So let's actually check if that's true. I'll rub out all the rest, and we're hypothesizing that these are the same. So next line, we have y equals 2 to the power of negative x. And that graph is in green. So those two graphs are the same thing. So there's two things that we'll learn, two things we've learned. One is the shape of this graph. The steepness of the graph depends on the number inside. And the next thing is that if you've got a number that's less than 1 for the base, it's got to curve downwards. It's curving downwards instead of curving upwards. So below your label for this downwards curving line, you can also add that this is the same as 2 to the negative x. So one way to understand that the graph is curving downwards is to understand that a fraction implies a negative index. The other way to understand it is remembering back to our graphing exercise, chapter 4, I think, when we had a negative value, when we had a negative sign in front of the x, that meant the graph was reflected from left to right. Okay, that's the other way to remember it. When you've got a negative sign in front of x, it flips around. Okay, So we've covered what happens when you've got a number that's less than 1 in our base. So what we're going to do is work on a few other transformations. So I'm going to place a rule on the board now. Y equals -2 to the power of x. There's a negative sign in front of the 2. There's a spoiler alert. The effect is the same no matter what the rule of the graph is. It does the same thing. So what do you think it does to this graph? If it's a parabola, then it makes the parabola flip upside down. Yeah, it reflects it around. So that negative sign reflects it across the x-axis. So let's check if that's true. -2 to the power of x. Okay, see, that purple graph has been reflected upside down. So we're going to copy down a few more graphs, but this time not as detailed as before. So just brief sketches, so you can see what's going on. Y, x, no rule is necessary. Write down your original graph, y equals 2 to the x, and then either using a dotted line or a different color, write down y equals -2 to the power of x. So that's where you have a reflection in the x-axis. Also worth noting are these y-intercepts. The y-intercept for 2 to the x is 0, 1, and the y-intercept for its reflection is 0, -1. Okay, we'll do a couple more. This time around it's 2 to the x, and then we're 2 to the x minus 1. We subtract a constant from the end. If you ever get stuck or wonder how to do it, just pretend it's a parabola and then try to apply the same transformation. It's the same thing. So what do you think happens? Shift it? Down. Yep, shift it down. So we should see the graph shifting down. Okay, see? And the purple graph has shifted down. So the y-intercept that used to be at 0, 1, now will be at 0, 0. We're going to make a brief sketch of that. Just a very quick one. Y, x, once again, our exponential graph, 0, 1, and then the graph where it's shifted down. Okay, at this point, I'm going to mention something that some of you may have noticed, but I haven't stated yet.
You can say
Angela?
it first and then I'll ask, because you might state what I'm about to ask.
Asymptote?
No, well, I was about to ask what happens if 2 minus 1 is in the bracket and then x is the power outside the bracket.
So -2 to the power of x.
No, so open bracket 2 minus 1, close bracket to the power of x.
Which is just 1 to the power of x.
Okay, yeah.
Okay, good question. Y equals 1 to the x. We'll do that thing later. Y equals 1 to the x.
Yeah.
What do you think?
Just does like this. Just go straight up.
Straight up?
Straight
across.
Why, so it is actually straight across. That's a great question. Thanks for bringing it up. 1 to the power of x is a horizontal line. Why is that though? What's 1 to the power of anything? 1. So it doesn't matter what x is, the y value will always stay as 1. So that's a horizontal line. Okay, but I will go back to 2 to the x minus 1. And the graph is shifted down. Now I mentioned asymptote before. So an asymptote is the imaginary line that the graph always seems to be approaching but never touches. Can you see how the asymptote that used to be along the x-axis has shifted down? Because the graph is shifted down, that means the asymptote has shifted down as well. Whenever you're sketching a graph and you know that your graph has an asymptote, you must always label that asymptote. So I will label as y equals -1. So let's do that here. label that asymptote, y equals minus 1. And what I haven't done on my graph is label these curves, so let's do that now. We've got y to the x, and, 2 to the x, and 2 to the x minus 1. We'll do one more, but with that example, the key is that when the graph shifts up and down, your asymptote will change as well. Okay, last one. This time around, I'll write it a bit bigger. 2 to the x minus 1. So I'm going to take that x, and then I subtract 1, and that's done first. So I'm going to ask you to predict what happens, and if you aren't very sure about what happens, just apply it to a parabola. It's the same thing that happens. If you know what happens, what do you think? Roman?
The asymptote will shift right on the x-axis by 1.
So it'll shift across.
Just about ask
Will
what
it change the height of the asymptote?
No.
No, so the asymptote will still be the same, but the graph shifts toward the right, and that's because of this thing going on. So let's check if that's true. So it's pretty hard to see. It's a bit more obvious when you look at the vertical part of the graph. The vertical part of the graph does seem to have shifted across by 1 unit. Okay, so that's the last thing we're going to label. I'm going to rub this off now, and we're going to do some examples with sketching these graphs. This can go always on. So just a very quick sketch to show what happens when we have a horizontal translation. We've got our original graph where the intercept is at 0, 1. And then we've got another graph that's shifted across by 1. Now, if the graph shifts across by 1, what used to be the y-intercept will also shift across by 1 as well. So the new intercept will be at 1. It won't be an intercept anymore, but this coordinate will turn into 1, 1. Now, we can also figure out what the intercept would be by subbing x for 0. Okay, and we'll do that later on in our exercises. So, a few key transformations to remember. One is where the base changes. If the value of a changes, that makes the graph steeper or less steep. If the value of a is less than 1, that means your graph is getting smaller. You're not multiplying a number to get it bigger, you're multiplying by a fraction to get it smaller. If you have a negative in front of the 2, that reflects your graph upside down. If you have a constant that's added or subtracted, that shifts it vertically. If you have a constant that's added or subtracted from the x, that shifts the graph right or left. And lastly, there's also an asymptote that we need to worry about. Yep.
Can there only ever be one x, like one unknown? Say if you put another x in like the bracket with the 2.
2x to the power of x.
Yeah, maybe.
Okay, you'll learn that in a bit later. This would be called composite functions when you've got multiple things going on. But not at the moment, we're just learning the basic parts. Okay, now I'm going to ask you to get your CAS out. I asked you to bring your CAS yesterday, and I'm going to ask you to graph y equals 2 to the x, then use CAS to solve 2 to the x equals 3 using graph. And as you do that, I'm going to set up the board for the next part. So the purpose is to try and use your graphing application to solve this equation. If you are not up to this step yet, what you would do is graph the first one, which is 2 to the x, then also graph the second one, which is 3. So you're going to have an exponential graph that curves upwards. You're also going to have a horizontal line that goes across. And where they intersect each other would give you the value of x. I'm going to come around to check whether you're up to that step. So the answer to this would be about 1.58. Is that correct?
Yeah.
1.58 for x? Okay, that's one way to do it. Obviously, there's an easier way and a better way, which is just place this in the solve tool in the calculator. Like solve open bracket 2x, 2 to the x equals 3, x, and that gives you an exact value, way better than an approximate value. Okay, but the purpose of doing this is the book will expect you to do that. So, we're going to go through some examples of sketching graphs. So, please copy down this. These examples are to graph and also label the range. So we're going to figure out what the range of these functions are as well. So it's f of x is equal to 2 to the x minus 1. In fact, we've done the exact same thing on a graphing application. Let's try and do this by hand. Now, the few things we need to label are always the y-intercept. You're always going to have a y-intercept when you sketch an exponential graph. Now, the x-intercept, it depends on whether your graph actually goes through x or not. Sometimes there won't be an x-intercept. We'll be able to learn when there will be an x-intercept or not in a future exercise. But for now, you always need to find the y-intercept. So let's do that. The y-intercept is when x is 0. So to figure that out, we sub in 0 for x. I'm going to use function notation, which implies that we've got 2 to the power of 0 plus 1, which is 2 to the 1. And it turns out that this is just 2. So the coordinate for the y-intercept is 0, 2. That's the y-intercept. Just make x 0 like you've always done. Now we also need to worry about the asymptote. Asymptote. All exponential graphs will have a horizontal asymptote.
You subbed x as 0, but wouldn't that be 0 minus 1?
Oh, yes, I made a mistake. I'm sorry. So it's x minus 1. So I'll change this. 0 minus 1. 2 to the minus 1 would then be a half. Thanks for pointing that out. Okay, asymptotes. If your graph hasn't shifted up or down, your asymptote should remain on your x-axis. The way we write this out as an equation is just the equation for that horizontal line, y equals 0. And then what you should also figure out is just one other point. We call it the dilation point to show how steep or flat the graph is. We've already used up x equals to 0, that's our y-intercept. So we choose another dilation point, taking an example when x is 1. So f of 1, subbing 1 for x, it'll be 2 to the power of 1 minus 1, which would be 2 to the power of 0. And 2 to the power of 0 is 1. So that dilation point is 1, 1. They're the three key features. Lastly, to help you visualize the graph, you should try and figure out whether the graph is increasing or decreasing. So I'm looking here, that base is more than 1, which means our number should be increasing each time. And that value of x doesn't have a negative attached to it, so it also means it hasn't reflected. So our graph should be going upwards. I'll call this increasing. Okay, that's all our information we're going to use. So let's sketch this graph. We're not going to need a table of values like before, we're just going to use our points that we've chosen. Firstly, we've got our asymptote, which is y equals 0. We've also got the y-intercept, 0, half. And then we've also got our dilation point. So when x is 1, y is also 1. So let's make that roughly the scale. So can you see how if the asymptote is here, and you've got 2 points, the curve should follow the points upwards. So that's all we need to do to sketch our graph. At the end, place a couple of arrows to show that they keep going. And here we've just completed our first graph. Let's label it as well. Y equals 2 to the x minus 1. Let's do another one. We have, one more thing I haven't answered.
In the rule,
Yeah.
wouldn't there be an asymptote 1 to the right?
If it's a horizontal asymptote, imagine shifting it towards the right. It still stays in that position. So the horizontal line still has the same width. Only if it shifts up or down, that's when it changes. I haven't answered what the range is yet. So the range is your set of y values. You need to look vertically along your graph to see where the graph starts and ends. Now the graph will start at 0, but not including 0. It always seems to be approaching 0, but it never hits 0. So our range, which is ran would be equal to, starts from 0 but not including 0, that's a curved bracket, and then it keeps going upwards forever. And as it keeps going upwards forever, we call that infinity. So the range is 0 to infinity. Another way to write it is coupled R with a little plus at the top. Great. So f of x is equal to 2 to the minus x plus 1. Okay, two transformations going on here. One is a shift, and one is a reflection. So, as part of what you do for your graph, you need to be able to visualize these shifts. So, let's work out the y-intercept first. We'll do this quickly. Y-intercept, I'm not even going to write down x equals 0 anymore. I'm going to go straight into my substitution. So f of 0 must imply that we've got 2 to the power of negative 0 plus 1, which is the same as 1 plus 1, which is 2. The y-intercept is at 0, 2. You can always find the y-intercept. Asymptote. Can you see how the graph is shifted? Which direction? Up or left? Up. It's shifted up because we're adding a constant number at the end. So the asymptote is, it shifts up, so the new horizontal line has the equation y equals 1. Dilation point, we pick another value of x apart from 0. Dilation, f of 1, and it'll be 2 to the power of minus 1 plus 1, which is a half plus 1, which is 3 halves. The coordinate would be 1 comma 3 halves. And lastly, you don't even need to write it down, you just need to consider whether it's a graph that's increasing or decreasing. What do you think? Is it increasing or decreasing? Decreasing? How can you tell it's decreasing, Stasha? It's correct? Yeah, there's a negative in front of the x, which implies that the graph is reflected along the y-axis. So it's a decreasing function. Let's sketch this very quickly. We've got y and x. Let's label our y-intercept. We've got one at 0, 2. We've got a dilation point at 1 and 3 halves, which is about here. 1 comma 3 halves. And also we've got an asymptote where y is equal to 1. And I hope you can see that if we follow these dots and make the graph approach the asymptote, we do have a graph that's going downwards. We've got 2 more to go. Range. Yes, thanks for reminding me. So the range. The range is your set of y values, but this time around the graph doesn't go all the way down to 0. So George, what do you think?
Would your range go back to
Yeah.
0?
No, it doesn't go back to 0, that's what I just said. So what do you think the range would be?
Goes and never touches all the way to 1, but it
1.
doesn't touch.
Ran would be from 1, but not including 1,
Yeah.
to what?
Infinity.
Infinity, great. Because you can see how the graph's going upwards, can't you? Okay. Last few. We've got f of x is equal to, let me decide if I want to skip this one. Yeah, skip this one. I'll do this. So we've got f of x is equal to negative 2 times 2 to the x plus 1. Okay, sorry. There you go. So we've got negative 2 times 2 to the x plus 1. There's also 2 things going on. Can you tell what 2 things are going on? There's a shift. Sonia? Up 1. Nikki? What else is happening? Can you tell? It's got to do with this part right here. Yeah, it is being dilated. It's kind of like our parabola. It gets a bit narrower. What about the negative sign? inverted, it's flipped upside down. So that's the shape we should expect to see. It should be a graph that's curving downwards. So let's do everything we've already done. Find the y-intercept, f of 0. So that would be negative 2 times 2 to the 0 plus 1. So 2 to the 0 is 1 times negative 2, that's negative 2 plus 1, and that's negative 1. The coordinate for the y-intercept is 0 minus 1. Next, we could find the asymptote. So the asymptote implies that the plus 1 means that the graph is shifted up. Asymptote. Y is 1. What else? Dilation point. Pick another number. So let's pick 1. 1's always the easiest number after 0. So it's negative 2 times 2 to the 1 plus 1. And what we've got is negative 2 times 2, which is negative 4 plus 1. And the answer is negative 3. The dilation point is 1, negative 3. And lastly, what else do we need? Just to have an understanding about which way the graph is facing. So it should have shifted up. The asymptote has gone up by 1, but the graph is going downwards. So, because it's going downwards, this time around, I'm going to leave more room on the negative side of my y-axis. Y should always be labeled at the top. Y, x. Give a bit more room for y because the asymptote is actually up there. Asymptote y equals 1. F of 0 is negative 1. So let's place that down. 0 minus 1. And we've got our dilation point 1, negative 3. So when x is 1, y is negative 3. Okay, and that's enough to sketch our graph. Follow your asymptote and make a curve pass through both points. Make sure you never cross the asymptote. Lastly, let's find the range. This time around, the range isn't going to go to positive infinity. Okay, what do you think?
What was the question?
Range. The set of y values. So where does the y value end and where does it keep going?
From 1, not including 1.
Okay, from 1 and not including 1. So there's a 1 with a curved bracket.
And infinity?
Infinity.
Yeah.
Positive infinity.
Oh, no, negative.
Negative infinity. Great. So it's negative infinity, comma 1. And you always place the lower value on the left side and the high value on the right side. The questions are questions 1 to 4, 5 ESO, and 6 for exercise 13C.